The scope of this framework is to show and illustrate the physical design methodology applied in this project. A quick synopsis about the ASIC design methodology, which consists of design entry, simulation, functional simulation, logic synthesis and test logic insertion, static timing analysis, simulation, gate level, formal verification, test structure verification, CMOS checks, floor planning, front-end processing, pre-layout, layout, final static timing analysis, post-layout, and ATPG and release to manufacturing. ASIC physical design methodology, the implementation for memory modules. The front-end mode consists of generating the SPICE models, which gives you the layout views and timing models. It also estimates power delay analytically. On the backend mode, it generates the SPICE models with layout views and timing models to perform DRC and LVS. It can perform at each level of hierarchy or at the end of the hierarchy, and simulates power delay, and it can also be back annotated. Fourth hit time reduction trace cache technique implemented in this design, this ASIC methodology design. A challenge in the effort to find instruction level parallelism beyond the 4th instructions per cycle is to supply enough instructions every cycle without dependencies. One solution implemented here is called the trace cache. Instead of limiting the instructions in a static cache block to spatial locality, a trace cache finds a dynamic sequence of instructions, including taken branches, to load into the cache block. The name comes from the cache blocks containing dynamic traces of the executed instructions as determined by the CPU, system on chip unit, rather than containing static sequences of instructions as determined by memory. Second technique for higher bandwidth in interleave memory subsystems. So increasing width is one way to improve bandwidth, but another way is to take advantage of the potential parallelism of having many chips in memory, and this memory chip can be organized in banks to read or write multiple words at a time rather than a single word. In general, the purpose of interleave memory is to try to take advantage of the potential memory bandwidth of all the chips in the system. In contrast, most memory systems activate only one, containing the needed words. Reducing cache miss penalty. Reducing cache misses is the main objective, but the cache performance formula assures the improvement in miss penalty can be as beneficial as improvements in miss rate. Many techniques to reduce miss penalty affect the CPU. This technique ignores the CPU, concentrating on the interface between the cache and main memory. The performance gap between processor and memory leads to the question, should I make the cache faster to keep pace with the speed of CPUs, or should I make the cache larger to overcome the widening gap between the CPU and main memory? The solution to this issue regarding cache miss penalties is adding another level of cache between the original cache and memory. That simplifies the decision to compensate for this issue. So the first level cache can be small enough to match the clock cycle time of the CPU. Yet the second level cache can be large enough to capture many accesses that would go to main memory, thereby lessening the effective miss penalty. Although the concept of adding another level in the hierarchy is straightforward, it complicates performance analysis. Definitions for a second level of cache are not always straightforward. Therefore, the average memory access time for this specific application of the ASIC device that I'm presenting in this video is average memory access time is equal to hit time of L1 cache plus miss rate L1 cache times the factor of hit time of L2 cache plus miss rate of L2 cache times miss penalty of L2 cache. The scope of this framework is to show and to illustrate the implementation of the floating point arithmetic unit, the arithmetic logic unit, the fixed point unit, memory, and the 5-stage pipeline architecture. Here I use the hierarchical environment. Timing-driven design is used. Each of the blocks is placed and routed separately with respect to the timing assertions. A second pass-through wiring connects the blocks together with respect to the chip-level timing assertions. Clock optimization and scan optimization process are applied to improve timing, wiring, and clock skew. Clock optimization modifies the organization of the clock tree buffers and the clock splitters according to the layout of the latches. The artificial intelligence floating point pipeline consists of 3 functional units: a floating point divider, a floating point multiplier, and a floating point adder. The adder logic used in the final step of multiply or divide. Double precision floating point operations can take from 2 cycles up to 112 cycles for a square root. In addition, the various units have different initiation rates. The floating point functional unit can be thought of as having 8 different stages. These stages are combined in different orders to execute various floating point operations. There is a single copy of each of these stages, and various instructions coding may use a stage 0 or more times and in different orders. This artificial intelligence neuromorphic CPU implements floating point by extending the pipeline length through the addition of multiple X stages for floating point operations, including its operating code and software models and algorithms. This introduces one complexity that may have not seen as simple stage integer pipeline, the possibility of instructions completing out of order. The extra length of the floating point pipeline means that unless we add new stages to the integer pipeline and thereby increase the number of bypass checks that must be done, an integer instruction can complete and write its results before an earlier floating point instruction completes. Physical design methodology for the ASIC 7 nanometer technology in the artificial intelligence system. First, identify connections to be optimized after placement so that they will not influence the placement. This include the scan and clock connection to latches. Second, generate constraints for placement on the basis of a timing analysis done using idealized clock arrival times. Add latches and estimates of wire load and RC delay before the physical design. These constraints include limits on the capacitance of selected nets and limits on the resistance of RC delay for selected connections. Three, perform an initial placement to determine an improved basis on constraint generation, and optionally to fix the placement of large objects. Fourth, generate new constraints for placement on the basis of a timing analysis done using wire load and RC delay values derived from the initial placement. 5. Perform the placement. 6. Optimize the clock trees and scan connections. 7. Make logic changes, including changes to circuit power levels to fix timing problems. Generate new timing constraints for wiring on the basis of a timing analysis done using the actual clock tree and wire load and RC delay values derived from the final placement. And finally, perform routing. Placement constraints. The area planner analyzes the distribution of the shapes and sizes of the library cells that take place in each macrocell and determines an optimal periodicity of circuit rows or columns and creates the placement structures based on each macrocell. This enables the placement functions to operate independently on different macrocells. The area estimation function described determines the appropriate width and height of each macrocell in the hierarchy based on the wire demand in the X and Y directions, as well as for any child cells or other descendants down the hierarchy that have rigid shapes. in order to fit each macrocell and its siblings macrocells into the parent macrocell in an effective way, the floor planning tool will have a range of legal shapes for each of the sibling macrocells. Bit stacking methodology addresses the need for greater chip density and performance when bit stacking is applied to designs with a high data flow content, such as in this case, such as processors using large arithmetic logic units, registers, multiplexers, and shifters. The utilization of available gates or density is improved. The design of a bit stack uses general methodology. First, data flow logic is logically separated from control logic. Then each data flow bit position, typically spanning numerous data flow functions, is isolated and its circuits are placed along the same circuit row, minimizing the amount of wire required for the buses. Placement can be used at several points in the design process, and different algorithms are correct depending upon the state of the design. Placement is often run before the logic has been finalized to obtain an early indication of timing and wireability. At this point, the feedback may be used to influence logic changes. This may also be the time at which the locations of large objects are determined. The basic algorithms used in our placement programs are simulated annealing and quadratic placement with iterative improvements. Both simulated annealing and quadratic placement accept many controls. They include pre-placement, for planning, specification of circuits to be placed in adjacent locations, net capacitance, and source to sink resistance constraints, and weights for the various components of the scoring function, including net length, congestion, and population balancing. This segment describes some of the coding guidelines. The system-on-chip ASIC designed software models were written in VHDL. The basic software coding rule is that in order to obtain predictable results, code was kept simple. Therefore, the VHDL software models were generated and written to guarantee that the synthesis would produce the desired result. In many cases, synthesis would not lend itself well to doing a custom implementation of logic, since the exact structure of the logic is basically unknown until after synthesis. Even then, the structure is not always what may have been anticipated. An example, a regular structure such as an adder may be very easy to envision and to lay out, since there is a high degree of parallelism among all of the bits of the adder. So the same adder when synthesized may not have this level of parallelism. Each bit can be constructed differently. This places some limits on the ability to do custom layout of synthesized logic. My choice of synthesis and timing verification for this project was Design Compiler. So two separate mappings were done. One mapping was performed during test insertion. The software model operated on a single clock. The timing model reflected the correct timing and load values for the actual LSSD macro. After the final transformation was done, the clock splitter was pulled from the macro and the two LSSD clocks were reconnected between the splitter and the latches, therefore partitioning the design in two areas. Chrysalis Design Verifier is a formal verification tool that I used in order to logically compare different versions of the ASIC gate level netlist. I used this tool to verify that the different versions of the netlist did not change functionally during the design process, such as test insertion, placement, and route. This allowed me to proceed without having to resimulate at each step. Functional verification applied in this project. The primary objective of functional verification is to ensure that this ASIC design meets functional requirements. The functional verification process and methodology consists of gate level event simulation, gate level cycle simulation, gate level hardware acceleration, Boolean equivalency checking, and power estimation. The objective is to show the artificial intelligence system on chip VHDL implementation of the 5-stage pipeline architecture. The processor system on chip unit is divided into three segments: the pipeline data path segment, the pipeline control segment, and the hazard segment, which solves all the problems of data hazards and control hazards. The instruction set for pipelining of the system on chip processor consists of fetching instructions in the first pipeline stage and decoding them in the second stage. 2. Reading the register file in the second stage at the same time that the hardware is determining what type of instructions was fetched required by the system on chip artificial intelligence unit. 3. Calculating the memory address in the execute stage and then accessed in the following stage required that memory operands appear. 4. Operands must be aligned in memory. 5. Instructions can be executed simultaneously in a single instruction cycle time. Each stage takes a single clock cycle, so under ideal conditions, the speed up from pipelining is approximately equal to the number of pipeline stages in the artificial intelligence system on chip. unit. The decode stage. In this stage, the processor decodes the instruction to produce the control signals and reads the source operands from the register file. The execute stage, the processor uses the ALU, arithmetic logic unit, or the multiply divide unit to perform required computations, which may be the calculation of values of two registers or address calculations. And the memory stage. In this stage, the processor reads or writes data memory, so only the LW and SW instructions use this stage. The system on chip SoC VHDL file defines a package declaration and body that defines the functions of the 32-bit and 5-bit register entity with clock and clear inputs, an instruction memory entity, and behavioral architecture. The instructions may have different bit patterns, a data memory entity, and a behavioral architecture, a general register entity, and behavioral architecture, two multiplexer entities, and behavioral architecture, the ALU entity, and the schematic architecture, and the 32-bit adder is compiled separately in this project. The instruction fetch stage is composed of three components: the instruction memory, the memory counter, and the instruction address adder. The instruction fetch is responsible for reading the instruction memory and sending the current instruction to the next stage within the pipeline. The instruction memory also takes inputs from the outside world that allow the loading of instruction memory for later execution. The decode stage is the stage of the pipeline where the fetch instruction is decoded and values are fetched from the register bank. It is responsible for mapping the different sections of the instruction into their proper and correct representations. The opcode and function codes are sent to the control unit, and the outputs of these corresponding components are then clocked and stored in the next stage. The execute stage is tasked for taking the data and actually performing the specified operation on it. The execute stage consists of the arithmetic logic unit, a determined branch unit, and the forwarding unit. The execute stage connects these different segments together so that the arithmetic logic unit will process the data, given inputs chosen by the forwarding unit, and it will notify the decode stage if a branch is taken. The memory stage takes the output of the arithmetic logic unit and puts it into the proper memory location if the instruction is a store. The memory stage contains the data memory object. It connects the data memory to register bank through the write back stage to read and also to forward on information about the current write back register. The write back stage writes the calculated value back to the proper register. It has input control lines that tell it whether this instruction writes back or not, and whether it writes back the arithmetic logic unit output or the data memory output. The arithmetic logic unit is capable of calculating the results of a wide variety of basic arithmetic and logical computations. The arithmetic logic unit takes as input the data to be operated on call operands and a code from the control unit indicating which operation to perform. The output is the result of the computation. So the ALU, the arithmetic logic unit, will perform the following operations. The arithmetic operations, that is addition, subtraction, increment, decrement, transfer, logic operations such as AND, NOT, OR, NAND, NOR, exclusive OR, and also exclusive NOR. The objective is to show the implementation of a 32-bit arithmetic logic unit using the behavioral model style to describe how the operation of the arithmetic logic unit is being processed. It is accomplished by using the hardware description language, the VHDL. The behavioral style makes use of the process statement. The process statement, which is the main construct in behavioral model, allows using sequential statements to describe the behavior of the system over time. So a process is declared within an architecture as it is illustrated in this video and is a concurrent statement. The statement inside a process are executed sequentially. So the process reads and writes signals and values of the interface, which is input and output ports, to communicate with the rest of the architecture, like other concurrent statements. As I have illustrated and shown in this video of the arithmetic logic unit, I have used several constructs to model the VHDL process statement. Also, I have used the when statement. In the case statement, it executes many sequences of statements based on the value of a single expression. Also, the case statement evaluates the expression in comparison of the value of each of the choices, while the when clause statement corresponds to the matching choice, which will make the statement to be executed. The finite state machine, FSM, is a paradigm mathematical model whose output is dependent not only on the current state of the input, but also on past input and output values. The state machine generated in VHDL, as I have presented in this video, are clocked processes whose outputs are controlled by the value of a state signal. The state signal serves as an internal memory of what happened in the previous iteration. Using the state signal, the finite state machine, the case statement contains a when statement for each of the possible states, causing the program to take different paths for every state. The when statement can also contain code which should be executed while in that particular state. The state will then typically change when a predefined condition is met.
The control logic drives the Fifo flag. Fifo empty, that is flags. No data is present inside the Fifo RAM. In the Fifo full, no data can be written to the Fifo memory. And Fifo almost empty / full is also supported. So the Fifo almost empty flags is when the Fifo is used in order to buffer input data stream of a device where the input and output data throughput is the same, but the timing is different, such as in input as burst data, output as continuous data. The Fifo is used to buffer the minimum number of bursts data in order to guarantee continuous reading from the Fifo without interruption. So in this case, the Fifo read control logic block checks for almost empty flags going high and set Fifo read control signals to read continuously from Fifo. In the dual port RAM model segment of the Fifo, it writes counter to address the right side of the RAM. It reads the counter to address the right side of the RAM, and the control logic aiming to update the right counter at each write data into RAM, and the read counter every time a data is read or is read from RAM.
The Fifo VHDL model has several settings and are configured to adjust the width and depth of the Fifo. The data width variables adjusts the size of the data in and data out buses so that one can write different sizes of bytes if needed, and the Fifo depth variable adjusts how big the internal memory of the Fifo is. In order to write data into the Fifo, first in, first out, first push the data onto the data in bus and then strobe the write enable input high for 1 clock cycle. It will write whatever is on the data into the Fifo's internal memory. Writing in bulk, the write enable signal is left high while changing the data on the data in bus each clock cycle. When the full flag goes high, this means the Fifo's memory is full and will not accept any more writes until data is read using the read enable input. If data is written while the full flag is high, it will be ignored. In the standard Fifo first in first out, when you write the first byte into the Fifo, nothing takes place on the data out bus until the read enable signal is pushed high for at least the clock cycle. Once the byte has been written into the Fifo, the empty flag will go low. To read the next byte from the Fifo, strobe
the read-enabled signal high for one clock cycle, and the next byte of data will be available to read the next clock cycle. When the last byte of data is pushed onto the data out bus, the empty flag will go high.
When modeling fixed-size RAMs, RAM memories, it's better to use an array variable rather than a signal for the RAM storage. On the right, the model looks to see if the address has already been used. If it is being used, the data is overwritten. If it is not being used, new storage is allocated for the address and data. So on a read, the model searches for the address given, and upon finding it, it returns the data. If the address is not found in the memory, then it returns the U for uninitialized. Also an X may also be a valid choice. So in the model that I just presented, it is shown the VHDL for the generic RAM core, which is the entity and architecture of the 16-bit RAM module and model, which instantiates the generic memory core, the RAM.
This segment deals with the layout design rules applied in this project as indicated and illustrated in the video. The goal of defining a set of design rules is to allow for a ready translation of a circuit concept into an actual geometry in silicon. The design rules provide a set of guidelines for constructing the various masks needed in the patterning process. They consist of minimum width and minimum spacing, constraints and requirements between objects on the same or different layers. The fundamental unity in the definition of a set of design rules is the minimum line width. It stands for the minimum mass dimension that can be safely transferred to the semiconductor material. In general, the minimum line width is set by the resolution of the pattern process, which is most commonly based on optical lithography, or E-lithography in this case. Hierarchical entities, macrocells, have dependencies on one another. For example, one cell may contain another. One cell may compete with another for area on the chip. Or a critical timing path may pass through two macrocells such that there is a constraint on the sum of the path delays through the two cells. The hierarchical timing closure for this design, the methodology was performed starting with the logical hierarchy, carry out manually or automatically, repartitioning the design to obtain the physical hierarchy. Perform quick floor planning and placement of the hierarchy. It provides a better starting point for timing planning. 2. Perform bottom-up timing abstraction generation. 3. Apply the top-down hierarchical timing closure methodology. If timing closure is achieved,
If significant progress has not been made towards the time enclosure, selectively flatten the problem blocks and either repetition them or leave them flat. I performed 2 major checks of the ASIC implementation illustrated in this video. It was performed before fabrication. So the first check is the design rule check, DRC, to ensure that nothing has gone wrong in the process of assembling the logic cells and routing. So the DRC is performed at 2 levels, since the detail router normally works with logic cell phantoms. The first level of the DRC is a phantom level DRC, which checks for shorts, spacing violations, or other design rule problems between logic cells. This is principally a check of the detail router. The other check performed is the layout versus schematic LVS checks to ensure that what is about to be committed to silicon is what is really wanted. An electrical schematic is extracted from the physical layout and compared to the netlist. This closes a loop between the logic and physical design process and ensures that both are the same. So the LVS check is not as straightforward as it may sound. However, the first problem with an LVS check is the transistor level netlist for a large ASIC forms an enormous graph. The LVS software essentially has to match this graph against a reference graph that describes the design. So ensuring that every node corresponds exactly to a corresponding element in the schematic VHDL code is very difficult task. The completion of routing finishes the ASIC physical design process. Global routing plans the wiring by finding the channels to be used for each path. The algorithms to find the shortest path are very similar. There are differences between global routing for different types of ASICs. 2 main approaches to global routing are one net at a time or all nets at once. With the inclusion of timing-driven routing objectives, the routing problem becomes much harder and requires understanding the differences between finding the shortest net and finding the net with the shortest delay. So different types of detail routing include channel routing and area-based or mazed routing. The most important points in the routing segments are: routing is divided into global and detail routing. Routing algorithms should match the placement algorithms. Routing is not complete if there are on-routes. Clock and power nets are handled as special cases, and clock net widths and power bus widths must usually be set by hand. So DRC and LVS checks are needed before a design is complete.